and he's going to tell us about seeing through the confinement screen.
All right, thanks. So yeah, I want to thank my co-organizers for the invitation, and also thank you all for coming on the holiday. So today I want to tell you a couple of papers and some work in progress I wrote with my amazing collaborators, Hao Chen, Xiaohui Liu, David Simmons-Duffin, Feng Yuan, and Huaxin. So the motivation for this talk is I want to ask the following question. So can we predict the number of particles that come out of a high energy QCD process? So in particular, I want to make some analytic predictions using the perturbation theory. So let's imagine you have some very high energy QCD state. So it's created by some, let's say some local operators. And this state has very high energy. So the central mass energy is much greater than lambda QCD. And so the state is going to contain a lot of quarks and gluons. And as they propagate out, they're going to split because of QCD interactions. So they'll keep splitting. And so if you try to naively predict the number of particles, you'll find a divergence. You might conclude you cannot predict the particles. But as we also know, as eventually this quark and gluon has to confine, right? So after hadronization, they will form stable hadrons. So the actual particles that will go out and reach infinity are these stable hadrons. So if you imagine you put some camera or some detectors at infinity in certain direction, and you just count the number of particles you receive at infinity, you'll get a finite number. That's just the number of hadrons that goes through the talking to. So you'll actually get a finite number. That's because that's just the hadron numbers. But this number of hadron depends on non-perturbative physics. So I don't know how to predict that. But there's one thing that I do know how to predict using perturbation theory, and that is how this number changes when you change the energy of the state a little bit. So the idea is if you increase, let's say you increase the energy a little bit, there will be a little bit more splitting happens during this process. And that is a perturbative process you can understand. So eventually I'll try to compute some quantity like this. It's like you can think of it as the scale evolution of the hadron number. And I want to predict it using perturbation. And so this is an old problem. It's cohadron multiplicity. It's been studied in old QCD literatures in the early 80s. So what happens if you try to use perturbation theory to study this quantity? What happens is that your naive perturbative extension will break down, and you'll need to do a resummation calculation. And a very interesting feature of the resummation result is that the leading term is proportional to square root of alpha s. So this is pretty strange, as you usually expect things to be proportional to integer power of alpha s in perturbation theory. But yeah, but that's what you get.
How does that come about from resummation?
So yeah, so the idea is you solve some evolution equation, and so this is like counting particles. But if you don't count particles, you count something like energy or energy to some power. You get a finite result. But then if you go to counting particle, you get a divergence. So what they did is they made some sort of power law assumption, and yeah, they made some power law assumptions, and then just assume a solution exists for particle number, even though you naively get a divergence. And if you do that, you can solve some self-consistent equation that gives you this square root of alpha. But so maybe a better answer is today I'll tell you a new framework that will give you this result and also generalize it. And this new framework will hopefully also give at least to me, a simpler conceptual picture of what's going on and why do you get this group. So, and that framework is running a matching of Larry operators, or detector operators.
This something difficult because you can't get the natural number out, or you get the change with respect to the log.
You get the change, yeah, but I don't know how to predict the actual number.
Natural number first.
Yeah. Well, at least using perturbation theory.
What was your question?
Like can you actually make the number?
You mean the concept of integration into one? But you can't predict it either. I guess you cannot.
So hydrogen should be an S-wave. You have only soft, you have only soft blue on this sheet.
Yeah, but eventually the thing that you measure are still hadron.
Some.
Yeah,
So you
I
got
think there isn't really a, yeah.
You got really
It's always low energies relative to confinement.
Yes, yes.
So you can never. So, but in practice, then people use this, like, how do they get the concentration? They just fit.
Yeah, I think they just fit. So they fit at one energy scale, and then they so evolve using this equation, and then you can see this sort of match the data.
So that CA is a computable number from perturbation.
Oh, yeah, CA is 3 again with QCD.
Although you said this, why is this proved?
Yeah,
You
so
said this, I'm sorry.
it's some result based on
That's supposed to be mysterious.
yes, but I'll give another explanation using the language of Larry operator.
Yeah,
That's one of the goals. Yes. So keep this square root in mind. All right. Sorry? Okay, so what is a detector operator? Well, roughly speaking, detectors are things you can measure at infinity or things you can measure in a cross section. And perhaps the most well-known detector is what's called the energy detector, or sometimes people call it ANAC. And essentially, you just measure things that, so this detector, you have to put it in a certain direction. So you put things at infinity in a certain direction. And essentially, the energy detector just measure everything that goes through the direction and then weight by its energy. So you can write it in terms of some non-local integral of the stress sensor, but also in free theory or perturbation theory, it's just given by this. The action on particle is just given by this. Like it only has support on particle going through the direction of the detector, and then you have additional energy power, additional factor of energy. So yeah, so this ANAC operator has very nice properties, like it's IR finite and it's positive and everything. But I'm not going to talk too much about ANAC, at least for the first part of the talk. But I'll be interested in this hadron number detector. That's the detector that measures this number of hadrons. So first of all, I'm going to use this null vector z to parameterize the direction of the detector. So yeah, it's just in this form. And for simplicity, let's work in the approximation that you should have 3 hadrons. And so for 3 hadrons, the definition is very simple. You just basically you have this a dagger a for each hadron, and you restrict the momentum such that it's along the direction of the detector, and then you integrate over energy with some standard phase mix method and some. So the expectation value of this thing in the state, in this very high energy QCD state, would be the hadron number that you measure. And for detector, it's convenient to talk about 2 quantum numbers. One is the scaling dimension of the detector, and the other one is the Lorentz spin of the detector. So the weight under the Lorentz boost. And I'll call them delta L and JL. And it turns out that this hadron number detector has the value of JL equals to 2 minus. Let's see. Perhaps, yeah, in this one, it's not very clear, I guess. So maybe one argument is, so this Lorentz boost weight. So first of all, these detectors, they depend on a null vector z. We can think of it as a coordinate on the celestial sphere, a d minus 2 dimensional sphere. And this Lorentz boost acts as a dilatation under on the celestial sphere. And the celestial sphere has d minus 2 dimensions. And so this is kind of just the dimension of that sphere.
I see.
And there's a minus sign. Yeah.
But NH of z is supposed to be an integer for each z. What kind of function is that?
It's not. I don't think it's integer. So I mean, idea is you integrate this over z, like over the entire celestial sphere. That's the total number. So it's kind of like density.
But if I were to do this in free field theory, at each z, it would be an integer times some perhaps delta function.
Yeah, in free theory, it would be dual.
You integrate with the celestial sphere or just some spatial sphere? These are all massive particles, right? Coming out.
So yeah, this definition is massless. Yeah, massless for massless particle.
Oh, so you're assuming they're extremely energetic. Effectively massive.
Yeah, so I assume they're massive, but later I'll write down a definition for massive part. You can also do it for massive. So yeah, so this is one example of detector, but since I want to do computation in perturbation theory, you might ask, can you define similar objects in vector QCD? And the answer is yes. And it turns out that the detectors that I'm going to define will be related to two important equations in QCD. One is the DGLAP equation. And so I'll define a family of detector related to this DGLAP equation. And the other one is the BFKL equation. So there's going to be another family of detector related to this equation.
Both.
Exactly. So there's only 8 people here. And yeah, and if you're not familiar with this equation, don't worry about it. I'll just name my detector after them because for other reasons. But okay, so I will tell you the definition of these detectors a little bit later. But let me first tell you their quantum numbers. So let me first tell you the delta L and JO of detectors. And the best way of illustrating the result to me, I think, is by plotting what's called a true Fauci plot. So the true Fauci plot, you plot minus JL minus 1 on the x-axis, and you plot 1 minus delta L on the y-axis. And one important family of detector on this plot is this 45-degree line. This trajectory, I'll call it the DGLAP trajectory. So each point on this trajectory is a detector operator. So it has, at any JL, you have a detector operator, and the delta L is given by just JO plus. So that's the DGLAP detector. And for example, the well-known A operator lives on this trajectory. And there's actually another important trajectory on this plot, which is this horizontal trajectory. This trajectory I'll call the BFKL trajectory. And it has, for any value of JL, it has the same value of delta L, which is 0. And finally, this plot has a left-right symmetry. So you can apply some integral transform that sort of flip this plot. And so each trajectory will have a shadow trajectory. So the integral transform is called spin shadow transform. So so the DGLAP trajectory will have like a shadow DGLAP trajectory going in this direction.
The shadow has a physical realization.
It's in some sense, yeah. I mean, you can define it like it's some integral transform of DGLAP detector, and you would, yeah. I think it's physical like so this is for free theory, so this is at 0 coupling, and you see that at 0 coupling there's a lot of intersection between these trajectories, and once you turn on interactions, what you'll find is that at these intersections, they will sort of just as you would usually expect for like there should be some sort of avoided level crossing phenomena. So they will the trajectory will sort of recombine and form smooth trajectory. So also here as well. So in some sense, the DGLAP and shadow DGLAP are connected after you turn on interaction.
What is the relation?
Real. I mean, for example, I think ANAC is kind of clear what you actually mean. Like you just measured energy, right? So
Is every real physical detector a detector in this sense?
that I don't know. At least some of them we can construct it like this.
But every real physical detector is sort of by definition an IR safe observable that accumulates all the amplitude. Seems close to the definition.
Yeah. So yeah, that's a very great question. Yeah. So I will try to address this in the next slide. Well, okay. Maybe I'll postpone answering that later. Yeah. Great. So yeah. So on this plot, you'll see these interesting intersections, and as we'll see later, once you turn on interaction, there's going to be some avoided level crossing, and it turns out that this point is actually the point that's related to this multiplicity problem that we discussed earlier. So we'll try to spend some time understanding what's happening around this intersection once you turn on interaction. And then there's also this important question that Bintel and Clay kind of asked, like, what's the relation between these QCD detectors that lives in like perturbative QCD and the actual things you measure in the experiment, like these, for example, hadron numbers or other things you can measure.
What were two and the other reference first
Approach.
when they made this plot?
Oh, well, so they made this plot in a different context. It's in Reggie physics. So it's actually, for them, it's actually m squared and j, and they found this linear Reggie trajectory. But somehow people just use this name for also plots for Lyra operators.
Or Frauch is the
Yeah.
other thing.
Yeah.
Difficult to pronounce.
Yeah.
Good. Okay.
And right, so we want to understand the relationship between these detectors and hadron multiplicity, and also we want to understand what happens when you turn interactions and look at one. So to answer this first question, we propose what we call a Lyra matching hypothesis. So the statement is that measurements at infinity in the theory of hadrons can be matched onto a linear combination of detectors or Lyra operators in perturbative QCD. So we expect some sort of matching equation like this, where you have some IR detector that measures hadrons, and you should be able to match them onto some UV detectors in QCD.
What is a UV detector?
Like this in free theory, like detectors you can write down in perturbative.
So there some integration over the local operators, the productivity.
Yes.
But these are
Why is that a hypothesis, not just a platform?
Why do you say it's a topology?
It's like you're saying you take a complete basis of operators in the UV, and the operators that you measure can be expanded in spaces. I don't understand what the assertion is. Like for local operators, we would have said this is a topology, right?
Oh, really? I was gonna compare it to local operator matching.
Well, I would have said that anything that the local operators at long distances could be expanded in terms of the local operators at short distance.
Oh.
Okay, maybe I don't know. Maybe I just have a misunderstanding.
Okay, I'll explain this slide, and maybe you can. No, well, definitely not in perturbation. Some perturbative information. Yeah. I mean, you can.
Why is this useful?
I'll show you later. So right. So let me contrast this with matching for local operators. So you can think of local operators as like a measurement at the point, like a point line measurement. And when you want to describe a point line measurement, it's most precisely described by UV degrees of freedom. So you can describe it using some local operators in your UV theory. And so this means when you compute this thing, correlation functions of UV local operator, it's well defined at any distance. You can compute it at a short distance, you can compute it at long distance. But we also know at long distances, there should be some effective description that so that you can approximately describe this thing using some IR local operator. So then you have some matching equation like this that match a UV local operator into some combination of IR operator.
Not the same CIs.
Not the same CI as well. Yeah, at the prime. And for detectors, the matching is in a different direction because detectors describe measurements at infinity. So measurements at infinity is most precisely described by detectors in the IR. And another way of saying it is that if you measure some IR detector in some state, it will be well defined for any state. So for example, this can be very high energy QCD state, or it can just be some high on.
If the infrared was gapped, say there are no detectors.
That's a very good question.
That seems like it seems to be.
That
What do you mean by IR there?
yeah, so
Like, do you really strictly mean the infinite distance limit of the RG flow? Probably not.
probably not. Yeah, so I think even if for massive particle, you can write down some detector at future timeline infinity. Like they live there. They don't live at no infinity. But I think you still expect they can be sort of expanded into.
What do you mean by DIR then? Like usually the extreme IR of the RG flow of a massive theory would be trivial.
That that's true.
So what, I don't understand what's meant by the equality. Like what DIR of Z is a light ray operator in which theory?
In something like this.
Say, ion.
Yes, yes. Pick your favorite EFT ion.
But does it differ from a free theory, which is a box space created by independent species of non-interacting particles?
In this approximation, it's this. I guess it's the same. Yeah, it's just a bunch of free. So, well, okay. So the hypothesis is, yeah, you can write this DIR in terms of some linear combination of DUV. And when you write this matching equation, you should use symmetry as your organizing principle. So if you have some symmetry that's preserved, both sides of the equation must be in the same representation.
So this discussion is primarily in the case of the Gatlin space. What do you think about it initially or both?
Yeah, but I think even in the IR, you use massive particles.
Even on the left-hand side, why a local operator is the things you would have done QCD or QED when you would have had dressed operators with some non-local cloud and soft photons or soft gluons.
Local.
There's not really local operators. They're all dressed objects that normally that produce some kind of S matrix.
What?
Why do you want to?
Imagine it's just QED.
QED, the correlation functions are totally fine. All of them.
But you wouldn't consider.
These are more like real.
Yeah, you wouldn't.
These are light ray.
These are
Like real.
But the correlation functions are
correlation function. You wouldn't consider correlation function of a naked electron, for example.
Well, naked electron is not a gauge invariant operator, right? But we never.
Like real.
No, you dress it. You have to dress it. You have to dress it with something like foolish, but we have a dress matrix. That's a very specific dressing example.
Look, I
Something
think he was
local.
discussing the correlation functions of gauge invariant local
Yeah,
operators.
exactly.
Those have a
It's
kind of.
already addressed, but
I know.
Oh, you
So, yeah.
powers.
On this side.
Powers of F, psi bar psi. The left is just those kind of operators that are manifestly well defined at points.
Yeah, those are the things you would measure. That's not
The correlation functions are measurable, so, but they're not defined. I mean, you have to do something fancy to get the S matrix. The correlation functions themselves are observable.
So you think, I would think about the detector is actually measuring stuff coming out of an experiment. Because it's an-
Yeah,
That's
that's
what's
what
on the
happened on
right-hand
this side. Yeah,
this is the light real.
yeah, this is this side. Okay, so
Then don't you have some analog of soft tissue? Unless you're
Well,
gathering.
but I think that the point is that the detectors are supposed to be a basis of IR safe operators. Like for instance, the average null energy operator is an IR safe observable, even in a gapless theory, even in an interacting formal.
Because it's not measuring particle.
It doesn't measure particle number.
If you're trying to measure particle, you have a problem. You have to have inclusive, something analysis,
Yeah.
inclusive cross sections. It's not.
I think it is the presuming he's going to explain.
yes, yes. So yeah.
Like this IR say.
Yeah, but they are supposed to be IR safe. That's supposed to be their claim to fame, is that this list of Ds on the right hand side are manifestly IR safe observables.
Yeah. Yes, that's the claim.
Yeah, I'm just wondering about the tension between, so in QED, there's a definition of the S matrix. It's semi-unique definition of the S matrix. But for QCD, gravity, any other more interesting theory, there isn't one.
Right, but here it's more like an inclusive observable one.
Yeah, an inclusive observable void.
Okay, so I mean, yeah. So yeah, the UV theory we're interested in is QCD and IR is hadrons. So they're related by confinement, and there's one symmetry that's preserved which is Lorentz symmetry, right? So no matter how complicated confinement is, it's Lorentz invariant. And that means if you start with some DIR with the fixed JL, everything that shows up in the matching must have the same JL. And for the number, for the hadron number detector, it has JL equals to 2 minus D. So that means all these UV detector must have the same value of JL. And you can do some dimensional analysis. Eventually, you will find that this quantity that we are interested in at very high energy will be governed by the QCD detector with the smallest value of delta L and with this value of JL.
What is suppressed?
They're suppressed by like lambda QC. Yeah, so I'm taking Q to be much greater than lambda QC. So that's what this library matching idea bites. You relate this thing to some to this delta L, which is just the scaling dimension of a QC detector. So you can try to compute this in perturbation theory.
Still Q. Overall, and
Yeah, Q is the scale of the state. Yeah.
And the extension is in I.
It's in, yeah, it's like a extension in lambda QC over Q. So so we want to understand this thing, and actually let me just tell you the answer. So previously I showed you that this true flux plot in free theory, and if you turn on interaction at one loop, this is what the plot looks like in pure Young-Mills. So I'm forgetting quarks for now, and so you get some so at zero coupling, the DGLAP and BFKL detector has this intersection, but once you turn off interaction, you get some recombined smooth trajectory. And to understand this multiplicity problem, remember we have to fix the value of JL. So all you have to do is that you just draw a straight line. You just draw this vertical line here, and the topmost point here that intersect with this this vertical line is the one that controls the scale evolution.
naively, maybe you again just a big picture question.
Yeah.
Naively, I will say N is not an IRC because I can make it approach.
In QCD, sure, but
Yeah.
but not for hadron.
Well,
So and this NH I define is really,
Number of hadrons.
yes,
It's gonna be
like I really put it at infinity. So I actually measuring hadron.
but there is some QCD scale here. You mean there is some QCD?
Yes. So in QCD, indeed, you can define something really also correspond to counting particle number.
So there's some resolution, something.
Exactly. Yeah. So in QCD, the operator that counts particle, the detector that counts particle number is exactly at this point, and you'll get some divergences, and actually it's a very complicated divergence because of this intersection. So and so yeah, there's some additional analysis one has to do to resolve this intersection, and then but the claim is you will get some, you can define some IR finite detector in every QCD, and that's actually just these 2 points. I'll explain in more detail here, hopefully. So yeah, so our goal is really just to really just compute the position of this point, because in perturbation theory. So
They don't care about the distribution.
for this observable, I don't. Yeah.
You just get the total.
Right. You can consider other observable, like compute that.
That's why I'm saying.
Yeah.
Total number.
Yeah.
So if you did this at 3 level without loops, those 2 points would merge.
These 2 points, yeah, they will just
They would
intersect. Yeah.
But the distribution would mean the correlation functions of this N as a function of CGN. That's
Right.
what you
Is that what?
Is that what you meant? Yeah.
Distribution is, yeah, hadron and yeah. And multiplicity of hadron.
Yeah, so I think you would get this from like the correlation, like not just the 1-point function of this N, but the correlation functions of this N as a function of different Z's.
Or
different thing.
Yeah,
But if you integrate, I think it's on the table. The total number of powers.
no, I thought the
What?
correlation functions, but maybe I'm confused, but I thought correlation functions of N of Z would be analytic functions of Z in bracket.
Because I can
Yeah.
make a collinear split, it doesn't also have the same day, and moves the multiplicity much lower.
Even after hadronization.
I know, like, this is all perturbative, I just do perturbative problem.
For pions or
Collinear splitting will talk.
for pions?
No, for quarks and radio cool.
Well, but that's perturbative QCD calculation.
Yeah, but that one shows you that this is not near.
If you write down QCD detectors, yes, so they have to be renormalized.
I don't.
So the process you described means if you try to
If I care about what are the number, what are the equation of P of energy of particles, not I don't think it's like collinear. Because you can make a splitting half. Right?
Yeah.
And that possible.
yeah.
If you remove one event from the hybrid to two event in the world.
So you say you're describing splitting for quarks and gluons.
Yeah.
So that means indeed when you define these QCD detectors, you compute matrix elements of them, you encounter all sorts of divergence. So we agree with that.
So you have to somehow define so that they you observe or don't change under that.
Yes, I was.
Then it's collinear thing.
Yeah, so I'll describe the procedure later. Maybe maybe we'll come clear there. Okay. You speed up. So yeah. So let me now. So okay. So just a few words about just general properties of detectors. So a lot of our recent understanding of detectors actually come from studying homophilia, studying CFTs. So it's realized recently that CFT data are actually have analytic continuation in spin, and it's actually this analytic continuation in spin is actually not just at the level of CFT data, but also you can do it for operators. And the analytic continuation of operators are what's called the library operator. And so so these things are defined by some sort of null integral of local operator. And the precise definition is not so important, but basically you pick a local operator and you pick a starting point X, you integrate it along a null direction Z. So that gives you this object, this non-local object LFO. One interesting property of this LFO is that it sort of exchanges the dimension and spin. So this LFO has dimension delta L given by 1 minus J, where J is the original, is the spin of the original local operator. And then JL is given by 1 minus delta. And it's natural to put the starting point X at spatial infinity. And when you do that, the null integral becomes the integral along future infinity. So you get some integral like this. And that's what people usually call detector operator. You just measure things at future infinity. And this detector operator sort of depends on this null direction Z, which you can think of as a coordinate on celestial sphere. And finally, I mentioned this spin shadow transform is just some integral transform on the celestial sphere, and you pick the kernel such that it changes the JL in this way. Okay, so now we're finally ready to define what the DGLAP and BFKL detectors. Let me start with free theory again. So zero coupling, just free particles. And also I'll assume pure Young Mills. So again, just gluons. So the definition is just like this. Again, you have this A dagger A, and you restrict the momentum to be along the direction of the detector, and you integrate it against E to some power.
So is there a gluon operators or
Yes, these are gluon equation operators.
not the glupo?
No, cool. Yeah, we're in perturbative cubes. And right, and you contract, and also right, also, and you contract. So A and B are like color indices, and you just contract them. Right. So And so you integrate over energy against some energy to some power. And it turns out that if you want the detector to have Lorentz spin JL, that power has to be minus JL minus 1. And so the physical meaning of this detector is that it's just that it measures flux as energy raised to power. And when the JL is some special value, it gives you the power, this power becomes 1, and that's the analytic operator. But you can define for any general continuous JL.
What's the range of the
It's when you insert it in some state, it's just some finite range because you have energy conservation.
what is the Q here?
In this equation, there's no Q. You compute matrix elements, then there's Q. And there's actually an equivalent definition for this object written in terms of a bilocal integral field string. So it's you take two f's and then you integrate them along this null line, again given by this direction z, against some special kernel. And you choose this kernel such that the Lorentz spin is JL. And you can show that in free theory, these two definitions. And when JL is some special value, you can also show that the DGLAP detector becomes the light transform of a local twist 2 operator, and that which then agrees with the definition in CF. So perhaps this makes it clear why I call it DGLAP detector, because that's the local twist 2 operator is controlled by these DGLAP equations. And so this is in free theory. And once you turn on interactions, you try to compute this thing. You try to compute some matrix element of this thing. You'll get IR divergences. And but so what the fact that you get divergence tells us this definition is not a good definition of detector in interacting theory. So instead, you should try to renormalize the spare detector and then get a well-defined DGLAP detector in interaction. So when you do that, there's actually a subtlety that I want to mention. So so let's recall when you do renormalization for local operators, what happens is that when you turn on interactions, the spin of the operator is fixed, but this delta, the scaling dimension is corrected, and you get some anomalous dimension, which people sometimes call space-like anomalous. And for detector, when you turn on interaction, the JL of the detector is fixed, but delta L gets corrected. So it's always the spin that's fixed when you turn on interactions. And for detector, you get some timeline anomalous dimension. But also remember, these two things are related by a null integral. And this null integral exchanges spin and delta. So if you look at this true-Fauci plot, what happens is that for local operator, you should think of the anomalous dimension as it's in the horizontal direction, whereas because it changes delta. Right? Whereas for detector, it's in the vertical direction because it changes delta L. So this is the anomalous dimension for a detector, whereas this is anomalous dimension for local. So there's actually some very well-known reciprocity relation between these two things, but basically it just comes from the fact that this is a triangle with 45 degrees. But yeah, so the point I want to make here is that when you talk about detectors, renormalizing detector, you should use JL as the Cohen number. So this is a bit different from a local operator, which will, and where you will use J as 1. So let's go back to this DGLAP detector. So as I said, once you turn on interactions, it has IR divergences, and that means it has to be renormalized. And but the story is very similar to how you would renormalize a local operator. You introduce some renormalization factor that cancels its divergences, and then you can go ahead and compute the anomalous dimension of these DGLAP detector. And
so it is normalized by an overall multiplicative constant.
Exactly. Yes. For generic JL. So for generic JL, it can be multiplicatively renormalized. And then you'll get some anomalous dimension like this.
QCP is divergence story of non-perturbative objects. That's not common.
elaborate on that? I'm not sure.
Shows you that there's some IR effect.
Well, but this is the fully perturbative calculation. This is just a
Yeah,
calculation in
but you
perturbative
want
QCD.
it- And this is usually absorbed by the pole. In the end, you have to match up.
Uh,
I think
yes, yes.
that's called a fragmentation.
Yes, that's exactly this what this C is actually.
Which is also correct.
Yeah, right. Yes. So this C is it's just this fragmentation function. Like, so you're right. Like the running of this thing
In
is
QCD itself, not correct.
well.
It's running itself.
Exactly. Yeah, well, so I think what you're saying is this thing is independent of mu. So right, the running of this thing is
It needs to be independent of mu, but
yeah.
it also,
So then the running just can't.
but I'm also just saying that the E part is not calculable.
I don't.
But
The C this coefficient C is definitely not calculable, but I think D is calculable.
well, maybe we mean different things, but yeah, but
Okay. Yes.
yeah,
So
but I think there is this probability of giving you a pattern. What's the probability of making a specific pattern?
yeah, that's fragmentation function. Yes.
That's not calculable.
That's not calculable. I totally agree. Yes. Totally agree.
Yeah, that's not the key.
That's not this thing. No. That's the matching coefficient.
Okay, that's what you call C.
Yeah. Yes. Yeah.
Okay.
Sorry, I wasn't clear. Maybe.
Yeah, but
That's why I
I
call
think in QCD, the divergence is the in the end, there's some divergence is absorbed by this non-perturbative function. That's what happens.
Right. Yeah. Yes.
I'm just saying, just adding a counter term, you have to say what are you normalized to.
Yeah. So the thing.
Counter term can be counter term plus a finite number also.
Sure.
So you are doing some scheme.
Yes, we have to. Yes, you have to pick a scheme. Yes.
What do you fix? What is the scheme?
I mean, for us, we just kind of like just MS bar.
MS bar.
I mean, yeah, you you just cancel the one over epsilon pole and then
Yeah,
yeah.
yeah. That's a little bit. I don't know. I mean, I'm just saying it's not arbitrary. You can add a counter term, but you have to be able to say what's renormalized. Counter term essentially is match up to some observable. That's what's renormalized, not just minus one.
Okay, but that is what you did.
But can I ask a clarifying question? So the multiplicative renormalization is independent of Z or depends on Z?
This no direction.
Yeah.
Is independent of that.
So yeah. You get a lot of information.
So yeah, so this is the anomalous dimension for the DGLAP detector, and this multiplicity, remember, it corresponds to J equals to -2 minus D. And so naively you will think, okay, I just plug in J equals -2 and we're done. But actually that's not true, because you will find a divergence. You'll find a pole at J equals -2. And this pole, actually, so a better way of understanding this pole is by looking at what's actually happening in the calculation. So the place where JL appears is that you integrate over energy, and then you compute this energy raised to some power. So, and the contribution that gives you the pole comes from the soft limit. So when the energy is very small, you can use leading soft theorem for this empty or form factor squared. And then once you do that, you'll find the energy integral exactly gives you this pole, J equals -2. And you have some remaining residue that looks very complicated. It's you have to sort of exchange, you have some color indices, and then there's some additional factor that comes from soft factor. But what this is telling you is that this thing is definitely not the DGLAP detector itself. It's the matrix element of some other detector. So we started with the DGLAP detector, and we computed its matrix elements at one loop. we find a divergence that is proportional to something else. So there's some mixing problem you have to solve. And that detector is exactly the BFKL detector. So here's the definition of the BFKL detector. It's a little complicated, but basically you start with this thing called NC. This NC is almost like counting number. You still have A dagger A, but you don't contract the color indices. Instead, you contract it with another FA. And so this gives you something with a single color index, which is not gauge invariant. To form something gauge invariant, you will need to do, at least have a product of 2 NC. But this product is not transformed irreducibly on the Lorentz group. But we want to have detector with a definite Lorentz spin. So you additionally integrate against some kernel to project onto some Lorentz zero. So that's the BFKL detector. It has some fixed Lorentz spin. And it also has some equivalent description in terms of integrals of field strength. In this case, you have Z1 and Z2, so you have 2 null lines, and then that forms a Wilson loop, and then you have 4 field strengths linked on that Wilson. With some complicated integral of these configurations. And it gives you a horizontal trajectory to properly plot, and you can again go ahead, turn on interactions and compute the matrix element of this thing at one loop, and you'll find that you get some anomalous dimension, which is given by this BFKL.
Why do you bring back the names every time?
BFKL? I mean, I have to give it a name, and for some other reason.
No, and you already found the.
It's all Russian.
Oh.
Well, if you have a better name, I'm happy to.
Very good. But no, forget.
So yeah, so these 2 detectors, the DGLAP and BFKL detectors, have a very interesting mixing structure. So this again, this 45-degree dashed line is the trajectory. This horizontal line is the BFKL trajectory, and at generic JL, both of them have epsilon pole proportional to itself. So and also I just argued that the DGLAP detector has some JL pole that is not regulated by Dirac, and this JL pole is proportional to the BFKL detector, and this comes from the self divergence. On the other hand, the BFKL detector, it also has epsilon pole proportional to itself, which gives you that BFKL anomalous dimension. And if you take that anomalous dimension and also plug in J equals -2, you'll also find a pole, and that pole is proportional to DGLAP. So they sort of mix to each other, and this pole is actually due to collinear divergence. And I don't think I have time to explain it, but yeah, feel free to ask me later. And also, finally, there's a third important fact, that is, at the intersection point, the 2 detectors become identical. And this you can argue using gauge invariance. So what this picture tells you is that when you try to renormalize the 2 detectors, you should just form a multiplet of these 2 detectors, and you renormalize the whole multiplet because they mix with each other. And an important fact is that they become identical at this point. So you have to perform some additional change of basis to make sure that the multiplet is non-degenerate at the intersection. But after this change of basis, you can just go ahead and do this multiplicative renormalization. And in particular, this renormalization factor, it should remove both epsilon poles and also the JL poles that appears here and here. And once you do that, the rest of the calculation is pretty standard. Eventually, you get some anomalous dimension matrix. And this is what the matrix looks like. So the interesting feature of this matrix is that at 0 alpha s, it's actually not diagonalizable. So you have some non-zero off-diagonal entry that shows up here, which tells you it's actually a log multiplet at tree level. And then once you add interactions at one loop, each entry gets some small corrections that's proportional to alpha s. So the structure of the matrix is like this, and then you can just go ahead and compute the eigenvalue of this matrix, and then you can see why you get this funny square root of alpha s. Basically, one of the eigenvalue looks like this. And if you expand it alpha s first, you'll get some anomalous dimension proportional to alpha s with its divergent at j equals -2. But instead, if you plug in j equals -2 first, then you just get the square root of alpha s here. So you can view this as some sort of efficient way of doing this resummation. In this calculation, you are just computing the eigenvalue of the 2 by 2 matrix. And you can go ahead and do some more complicated things, like you form this characteristic equation of this matrix, and then you just compute delta L at each value of JL. That gives you these loop curve, which is the space. You can think of it as the space of QCD detectors at one loop. And well, okay, this is pure Young-Mills, but for QCD you can do the same thing. You just have another trajectories from quarks. Okay, so this is nice, and now you can ask, okay, I want to go back to this hadron multiplicity problem, and can we make any predictions based on these the shape of this curve that we just computed? So I'm actually going to first define something more general, a more general hadron vector, which has general Lorentz spin JL. So it's again some A dagger A, but you integrate it against some special kernel chosen to have fixed Lorentz spin. And when JL equals 2 minus D, you reduce it to counting particle number. But this is some more general definition. And but if you go through the same library matching idea, you can get this equation. Basically, the scale evolution of this thing is controlled by the QCD detector with the smallest delta L and with the same value of JL. And so in this equation, the right hand side is something you can compute in perturbation theory. We just did. On the other hand, the right hand side is something you can try to extract in data, whether from numerical simulation or from experiments, right? So you count the particle numbers, and then maybe for several different values of Q, and then you compute this derivative. And this equation also depends on this value JL, this Lorentz spin. So this JL is like a control knob for the experimentalist. You can change different JL, and by changing the JL, you can sort of compute different delta L's, and that allows you to sort of see the shape of these leading trajectories of QCD in data. So that's what we did. We tried using this Monte Carlo event generator PCL, and it basically it generates a bunch of data that allows you to compute the left-hand side of the equation. And that's the green and red curves, where the two curves just correspond to two different states. And the blue one is the analytic predictions for the trajectory that come from solving this characteristic equation for the dilatation matrix. So you see that it agrees pretty well. And so this is the point corresponding to ANAC, and this is the point corresponding to multiplicity. So I'll view this as at least some evidence for this, our library matching hypothesis, and also our picture for the DGLAP and BFKL. And the reason why the analytic prediction has some uncertainty is because when you compute the left-hand side, you have to change Q. You have to take the derivative, so you look at the data at several different values of Q. And when you change Q, alpha S also changes. And the analytic prediction depends on the value of alpha S. There's some range for that. And you can go ahead and do something perhaps more realistic. So for example, in actual collider experiment, you have to introduce some jet algorithms that group different particles into jets. And jet algorithm breaks Lorentz symmetry. So you might expect our analysis doesn't work, but somehow it's still a very mild multiplication. So and the results still agree pretty well. But and then you can ask, can you do it for actual collider data? And there's some publicly available data from CMS, so you can take that and try to make this plot. And unfortunately, it doesn't agree. But I think it's expected because of the issue is the state. So our analysis assumes the state is created by a single local operator, and that is just not true for PP collision. So in particular, there's some additional energy dependence from like quark and gluon fractions in PP collision. But yeah, I think it's expected that once you incorporate these things, like from PDF, you should be able to match it better. So I guess I'm out of time, but almost. I will.
So PCF has the DGLAP evolution implicitly.
Yeah.
Yeah,
So
it
Upper
is
shower. Upper shower.
the partnership.
yeah.
Are you doing something beyond this year?
Not
year
at this
in
stage.
essence, it's also a calculation. But you're just doing DGLAP currently. Run the upper shower.
Yeah, but I mean, first, yeah, I mean, this region is not just DGLAP. It's really a mixing between DGLAP and BFKL. DGLAP, if you plot DGLAP, it would diverge.
But this year, eventually, just the outcome.
Yeah, I agree. So yeah, so a better thing would be try to match this curve from CMS data, but because of the issue with the state, we haven't been able to do that.
Well, you can also try to measure. Doesn't the PCA data also have arc versus the wall?
Yeah, but you can ideas you can choose to not have it.
Oh,
Right. So you can choose the state to be like just a single local operator. That's how, yeah, that's how we got this thing. So I actually I might want to skip some of these things. So yeah, we focus on this direct intersection, but you can also from a similar analysis for other intersection. So you can get some plot like this, but I'll skip this. And also you can also explore this in the complex plane. So we saw that because of analyticity and spin, these detector operators are expected to make sense even for complex JL. So you can ask, can you also plot it? And so there's some calculation that was done, like in planar equals for finite coupling, they use integrability, they can also make this very nice plot. And so what you expect to see near the intersection is that you will see some branch cut and branch point structure once you go to once you have non-zero imaginary part of JL. And you can see some similar structure even also in Wilson-Fisher. And again, this is very preliminary. You can also observe this behavior in PTL data, and actually for CMS data as well, although I didn't show here. So if you plot so if you go to imaginary direction of JL, and then you plot the imaginary part of delta L, and you'll see this jump, which indicates branch cut and structure, and then also there's some branch. So you can also take CMS data, and even it doesn't match very well because of the issue with the state, but you can still see a branch cut in the data. So I think this is kind of cool that you get to see like actual analyticism and spin in data. Okay, so in my remaining -5 minutes, I will talk about something else. Hope
You can talk about the shadows.
Sure.
Yeah.
Yeah, in the minus time. So we introduced this library matching idea, and you can ask, okay, you predict this hadron multiplicity or some generalization of it. Can you use it to predict some other things? And one very natural candidate is the energy-energy correlator. So the energy-energy correlator is just like a 2-point function of A9 operator. And so you can write it in this way, or you can also write it in perturbation theory. You can write it in terms of some weighted cross fit, where you insert some additional power of energy, and then but you also restrict the it's like you put 2 detectors at very far away, and then you measure energy, and then now the observable is just a function of the angle between these 2. Okay. And the nice thing is because energy is conserved during splitting, so this observable doesn't have any IR divergence. It's just an IR finite output. So you can go ahead and measure this thing in QCD. So I'm going to use this cross ratio Z to parameterize the angular dependence. So Z takes value between 0 and 1. So the 2 interesting kinematic regime is when first, when Z is close to 1, that means the two detectors are almost back to back. And also when Z is close to 0 means the two detectors are almost collinear. So you get some interesting shape in QCD. And it proves very different physics, like in this region, it's some Sudakov, it gives some Sudakov double block, and in this region, it's some, you get some parallel behavior, and also eventually become free hadrons. So recently, this observable has received a lot of interest, as you can see from the citation history of this first EEC paper. And
oh, that is the first page. So,
right, so yeah, it's the, yeah.
not the one who produced it.
Right.
That was biased.
So yeah.
Okay, so why? Why did
Why?
the internet space so suddenly?
I think several reasons. So the reason why it decayed first, okay. So the reason why it decayed first is that it got first introduced, but I think at that time it's hard to measure experimentally. Experimentally it's hard to measure it. For a reason I don't fully understand, but apparently recently there's some development that you can measure, and also because it was realized that you can write it in that form, which is in terms of correlation function. So that allows you to use a lot of technique from formal theory. So it's a very nice there's some very nice connection that connect formal theory and phenomenology and everything just by studying this observable.
Didn't understand that.
Exactly. Yeah. So yeah. So he's here. So yeah. So I'm gonna focus on this region where in the collinear limit where the two detectors become very close to each other, and in this region there's an important energy scale. The square root of D times Q. So it's not just Q itself. There's also some energy dependence. And so Z is always small. But there's also this factor. So ZQ squared can be much greater than lambda QCD. So in this region, you still have a perturbative description. So Z can also be extremely small, such that ZQ squared is much smaller than lambda QCD. And in this region, you just get the physics is just a bunch of hadrons. So you just get some free hadrons, and that gives you this plateau. Sometimes people call this pre-confinement region, and the plateau is like the post-confinement. And so the pre-confinement region is it's just perturbative QCD. So the Z dependence and Q dependence are you can completely describe it using basically you can derive an OPE between these two analytic operator, and that just tells you the shape of this curve. On the other hand, in the post-confinement region, the angular dependence is just a plateau, like it's a constant, because the picture is just like you just have a bunch of hadrons that don't interact, so you just get some uniform distribution. But the question I want to ask here is, can we also predict the Q dependence of this plateau? So if I change the energy of the state a little bit, the plateau is going to move. Can I predict how this plateau moves once I change the energy? So maybe you can kind of guess what I'm going to do. The height of this plateau corresponds to some measurements in the IR and some IR detector. So I can identify what this IR detector is. In particular, I'll identify the Lorentz spin of that detector, and I'll just match it onto QCD detectors. And the Q evolution would just be the anomalous dimension of that QCD detector. So I guess I don't have time to explain this, but basically, yeah. So yeah, basically what I said, you can identify that the height of this plateau is some sort of double twist operator of ANAC in theory of hadron. And in particular, that operator has JL equals -6. So again, what you have to do is that you match it on QC detectors by drawing a bunch of vertical lines on the true-Fauci plot. So this is the leading operator. It matches to DGLAP detector with JL equals -6, and you have some other detector. So so the conclusion is the leading contribution should come from this particular DGLAP detector. And you can again see this in PTF, where you basically have the data, and then you fit the data with this curve at some energy scale, and then you change the energy scale, and when you change it, you use the running of this DGLAP detector, which you compute analytically, and that gives you some prediction, which you can see agree pretty well with the data. So this is kind of another application of this library matching idea. All right, so let me conclude. So we sort of we explore the space of QCD detectors at one loop, and we resolve these mixing between trajectories, in particular DGLAP and BFKL. And I argued that you can match a bunch of measurement collider observables like in hadrons to QCD detectors, for example, hadron multiplicity and also this collinear plateau of EEC. And yeah, and you can make predictions using this library matching idea, which had good agreement with simulation. So there are several natural directions. For example, you can try to improve the comparison with CMS data, and you can try to ask. I think we certainly haven't explored the whole space of detectors in perturbative QCD. So can you study sublink trajectories, or is there some more generalized factor? And finally, there's on the more formal side, I personally would love to understand better. Can you derive some sort of algebra OP of these general detector operators? So yeah, and that's all. Thank you.
In your when you showed the EEC just now,
Yeah.
So I understand you're using the data of one of those ones to predict the other two. Is that right?
Yes. So basically, so our prediction is that it is controlled by these operator, and each operator has different angle dependence, right? So this one has theta 0, and this one has theta squared. Right? So the idea is you at a fixed energy, you fit the coefficient in front of each operator using the angular dependence, and then you change the energy and you just run each operator, and then that gives you some prediction, which.
And then your other plot where you showed the one where you got uncertainty from the alpha n.
Yeah.
From the 13 alpha. Can you like? Can I conversely like use this to measure alpha s? And is that useful at all?
This one, you mean?
Yeah.
Yeah, this one is a bit hard. I think it's because like the dependent is square root, so it's kind of a bigger thing. We actually propose to use this thing to measure alpha, like the height. No, this is just a number, and you change it. It has some dependence on alpha s because it shows that alpha s. Alpha s at what scale? Well, yeah, it's a good question. Yeah, you do have a. So I think you have to make a choice, and that choice gives you the uncertainty, some uncertainty on the alpha s, the value of alpha s.
No, let's thanks for